Pausen. Good afternoon, hey. Good afternoon. Good afternoon.
Oh, you've upset Howard. He was hoping for most wonderful.
Good afternoon.
Okay, most wonderful good afternoon then.
Good afternoon, sir.
Thank you. Most wonderful good afternoon. Good afternoon.
Yeah, so if something does go, yeah, that's it.
Good afternoon. Most wonderful good afternoon. Most wonderful good afternoon. Good afternoon. Good afternoon. Good afternoon. Most wonderful good afternoon.
Yeah, you get to afternoon.
Most wonderful good afternoon. Good afternoon. Most wonderful good afternoon. Good afternoon. Good afternoon. Good afternoon. Good afternoon. Most wonderful good afternoon. Thank you. Most wonderful good afternoon. Good afternoon. Most wonderful good afternoon. Good afternoon. Most wonderful good afternoon. Good afternoon. Good afternoon. Good afternoon again. Good afternoon. Most wonderful good afternoon. Most wonderful good afternoon. Thank you. Most wonderful good afternoon. After morning. Afternoon. It is afternoon. Very good afternoon to you.
Yeah, and if they're American, they're better.
Most wonderful good afternoon.
Good afternoon.
Good afternoon. Problem sorted?
Yeah. Oh, that problem.
Yeah. Good afternoon. Most afternoon, wonderful good afternoon. Oof, can't speak properly anymore. Good afternoon. Most wonderful good afternoon. Good afternoon. Good afternoon. I like the chicken wing thing. Good afternoon. Good afternoon. Most wonderful good afternoon. Good afternoon. Good afternoon. I have a little counter here that counts how often I say afternoon. That tells me how many students are in the lecture.
I don't know. I don't know what happens to these things that you could do these days.
I suppose you can do it,
Yeah.
but yeah.
You know, you've got little counters and
Yeah.
things going in. Computers these days, they do everything. Yeah.
Most wonderful good afternoon. Most wonderful good afternoon. Well, let's get started. Okay, most wonderful good afternoon, ladies and jelly beans. Lovely to see so many of you. on a horrible Friday afternoon. Well, horrible in terms of weather. Although people say there is no such thing as bad weather, it's only bad clothing. But, you know. In this session, I want to, bless you, I want to briefly discuss with you what you're going to do in the next 2 weeks. And I also will tell you a little bit about the assessments in this practical, in this module. So, the BI 308 module, unlike most of the other first-year modules, actually has 3 components of assessments in the coursework and the exam. The exam counts for 50% of your... Sorry? Louder. I'm shouting already. Can you hear me? Okay, good. Okay, I try to speak loud. Yeah, thank you for telling me. Okay, so there's the exam, and there are 3 pieces of coursework. One piece of coursework you are going to do in week 8, that is the assessed practical, and that counts for 20% of the module mark. In the last week of December, you are going to do an in-class test. This will be a problem-solving test. So, for example, I give you, well, I want you to make up a buffer. What do you have to weigh in? And you might need to do a little bit of statistics as well. Everything is covered. This in-class test will be open book test. That means you can bring in whatever resources you deem necessary. You can write cheat sheets until you are blue in the face, can bring them in. You can do a summary of all the equations, whatever, right? The only thing that you can't do in this assessment is you can't use the internet, and you can't phone a friend or ask somebody else to do the test for you. Okay, so this is what we are going to do this year. And then in the second term for this module, you will get 15 multiple choice tests. They are online tests. And I have not yet totally decided on how I'm going to play it, whether a test or whether I give you them all in one. I need to see how I feel about it. You can do them in your own time, and you can do them as often as you like. You will get immediate feedback, but you won't get the correct answers, of course. And I think the way I'm going to play it this year is that the average of all your attempts will be counted for the mark. Each test will count for 1% of the coursework. It's not a lot. There's a little bit of psychology behind that number, but I'm not going to tell you that. And these tests will cover basically everything that we have done in this module. So there are 15 of them. So as you can hopefully do the numbers, 15 multiple choice tests, that's 15% of the module. The in-class test in December is 15% of the module. The assessed practical is 20%, and the exam then is 50%. You do not have to pass every single assessment. although it would be good. It is enough if at the end, coursework plus exam, you get an overall of more than 40%. If you get more than 40%, you've passed the module, right? Make sense? Good. Any questions so far? Brilliant. Okay, so what are you going to do in the practical next week? That is not the assessed practical, but it is a practical where we expect students to be present. I know it's enhancement week, and people just simply bugger off. That's not the intention of the enhancement week. And the practical is there, but you don't have any Friday afternoon session with me. I don't know if you've got any other do you have any other lectures next week? No. Okay, so it's only the practical. Sorry about that. Okay, next week's practical deals with pH and buffers. And as you can, I think I've sent out the links to the instructions. You all should have these 5-6 pages that I handed out right at the beginning in the first practical. Please bring them along, you need them. But you also find them in the links that I emailed you. So if you've lost yours or if you haven't got one, you can easily print that out. Yeah? As I said, the practical deals with pH and buffers, and one of the important thing is I want you to be safe in this practical. We are dealing with acids, we are dealing with strong bases, and you must wear gloves, lab coat, and safety specs. That's not negotiable. And last year, I'm afraid I had to throw a student out because he persistently refused to wear safety specs. Oh, sorry, I forgot. Oh, sorry, I forgot. Well, you probably won't forget when you are blind. So please, 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 I don't take any prisoners with that. If people fail to follow these simple safety instructions, there's the door. Sorry. But you will be all good, so I don't have any problems with you. So let's see what you have to do. There are a number of tasks that you're going to do, and first of all, you have to make some stock solutions of 2 buffer components. And you have to calculate how much you have to weigh in. Basically, what you need to do is you have to make up 50 milliliter of 150 millimolar KHPO4 solution, and the molecular weight for that is, what is it? I think 136.1 gram per mole. So you have to calculate how much of this substance you have to weigh in to get this 50 milliliter of 150 millimolar solution. And if you are smart, and I know that you are smart, because otherwise you wouldn't be here, if you are smart, you do the calculations over the weekend. This weekend, I mean, so that you don't stress out when you have to do the thing in the practical. You also have to calculate the amount of grams that you need to weigh in to make up 50 milliliter of a 150 millimolar disodium phosphate. And here the molecular mass is, what is it? 142.1 grams per mole. And the way you do that is you weigh these substances in on some scales. You use what is called a weighing boat. That's a little plastic container, if you like. And I'll show you then in the lab where they are. You weigh in the correct amount. You add around to each one of these substances. Oops, what have we got here? Around it's interesting. My pen doesn't work. Okay. Around 40 milliliter of water you add first, and you need to dissolve the substance totally. There should not be any crystals floating around. And then you have what is called a volumetric flask, which looks a little bit like that. It has a line, a calibration line here, where it says 50 milliliter. You put your 40 milliliter of solution in that flask and then fill it up to this calibration line with distilled water. This gives you exactly 50 milliliter of your component of the Na2HPO4 and the corresponding other one. Now, these are two components. If you completely ignore the sodium and the potassium, you can figure out that these components are conjugate acid-base pair. You've got H2PO4 minus and HPO4 double negative. Why are they conjugate acid-base pairs? What's the reason why I say that they are conjugate? What's the difference between them? It's don't go with the charge. One proton. The difference is one proton. So this one here, is that the acid or the base? Must be the acid, exactly. So this one can give off a proton, and we get the double charged phosphate for that. So we've got this one here, the acid, this one here is the base, the conjugate base. So you have to make up this solution. Do you actually measure the pH? Yeah. You then are required to measure the pH of these two substances. And to do so, we have special equipment. This is called a pH electrode. Looks a little bit like that. Forgive my drawing skills. This is a highly sensitive piece of equipment that you stick into your solution, and by some kind of magic, well, it's not magic, it's just simple physics, it will measure the proton concentration. It's connected to a device, and this thing will then show you the pH. This thing is already calibrated, so don't mess around with any knobs or buttons or anything like that. Just use the device as it is. And before you use this device, you always have to sort of clean it. That means you just rinse it with distilled water. Rinse with water. And then you sort of dry it a little bit with some tissue. This is just simply to avoid any contamination with a liquid where you have used it before or somebody else has used it before. So every time you want to use it, rinse it, dab it dry, use it. When you have taken the reading, rinse it, dab it dry, put it back into its storage unit, and that is usually just simply a salt solution. It should never be without any liquid, because then it runs dry and it doesn't work properly. These things are not cheap. A normal pH electrode is about 150 quid. They're made of glass, so may I ask you try not to break it. It would be very appreciated. And you will use a mixer and a stirrer. The stirrer is just something that looks a little bit like a small white magnetic stirring bar, like my Apple Pen here, but much smaller. And that just simply helps to mix the solutions that you are producing. Make sure that whenever you use the mixer, you turn it down first and then slowly increase, because otherwise, if you increase it too fast, then the little stirrer, also called a flea, will start to do weird things, and it will probably either break the glass because it's spinning so fast, or it will just take off and fly away. So please don't do that. And pH electrode and these little magnetic metal stirrers don't mix very well, because this stirrer, this magnetic flea, has the annoying habit of, when it is spinning too fast, it will destroy, it will crush the pH electrode. So again, please avoid that. In the last 2 years, touch wood, we had no destruction, and I'd really like it to stay that way. Okay? Happy with that? Brilliant. So, you are measuring these two solutions that you have, and hopefully you will find that one is the acid, the other one is the base, and hopefully that matches with your predictions. What you then do is, let's go back. You take one of the solutions. Let me quickly check which one it is that you need to take. So you take 25 milliliter of the acid in a beaker, and so 25 milliliter of the acid in a beaker with a magnetic flea, and then you add stepwise, and I would suggest you probably use half milliliter steps. You add half milliliter of the base and measure the pH after every addition. It's called a titration. And you do that, and you record how much of the base you add. You do that until you have reached pH 6.5. Record the volume of the base that you've added. That's one thing. The other thing is we want to actually know if predictions are correct. So what you're basically doing here is when you mix your acid and the base, you create a buffer. And remember, we have the buffer equation, the HH equation, Henderson-Hasselbalch equation. Which says that you have pH equals pKa minus log of the concentration of the acid over the concentration of the base. And if the log doesn't have anything, it's by definition it's log to the base of 10. Now we add acid, we add base, so we have a buffer system. And what you're basically doing is you try to figure out how much of the base do I need in order to get the pH of 6.5. That is what you're doing in this titration step. But what we can also actually do is we can sort of try to figure out first how much acid, how much base do we need, mix that, and then see if we get the right pH. And you can actually do that. You can already, in preparation for the practical, so before Monday, you can calculate what is my ratio of acid to base. pH equals pKa minus log, and I just simply write ratio. What is my ratio of acid to base if I want to have a pH of 6.5? 6.5 and the pKa is 7.2. That's the pKa of the acid in this case. And you can calculate what is my ratio. Those of you who went to the logarithm workshop earlier today are going to have a laugh because we've done that already. if you didn't go, well, I'm sure you can do it, or you just simply look at the recording, which I will put up on this little sheet and on YouTube. So once you've calculated this ratio, you just simply do this ratio. So let's say the ratio is acid to base. The ratio is hey, let's think for a moment. Let's think for a moment. We want a pH of 6.5. We have a pKa of 7.2. Do we need more acid or do we need more base to get this pH? What do you reckon? Do we need more acid or do we need more base? Who says acid? Acid? Why? Why do you think we need more acid?
Because when we add an acid, the pH would go low.
Okay, so if we add an acid, the pH will go down. You're absolutely right. But is she right in terms of saying we need more acid than base? Let's think about it for a moment. Let's say we have, again, by the way, you are right. pH equals pKa minus log acid over base. If we have the same concentration of acid and base, if we have the same concentration of acid and base, we can say pKa minus log. We can basically write this as 1. If it's the same concentration of acid and base, they cancel out, and all we have left is 1. What is log 1? 0. Log 1 is always 0. It doesn't even matter what base you have. The base here, I mean, in this case it's log 10. It doesn't matter whether it's log 2, log E, or whatever. It's always 0. So in this case, our pH is equal to pKa. In other words, if you have the same concentration of acid and base, your pH will always be the same as the pKa. And that is actually really, really useful if you want to do a sort of a reality check. You don't need to do wild calculations. You can just simply say, right, my pH is lower than the pKa. Or let me write this like that. My pH is smaller than the pKa. This means need more acid than base. If the pH is larger than the pKa, then we need more base than acid. So if I ask you in a test to make up a buffer, the first thing that you need to do is really check, what do I need? Is my pH lower or higher than the pKa. If the pH is lower, I need more acid. If it's higher, I need more base. Pretty simple. But this will save you lots of precious marks, because sometimes people do weird things and they got the ratio exactly the wrong way round. Instead of, let's say, 5, they get a ratio of 1/5. However, if you do this check first, you can say, oh, wait a moment, there's something not right. My ratio says something completely different compared to that, so therefore, double check. So, what you need to do is you need to calculate the ratio of your acid and base so that you have 6.5 equals 7.2 minus log ratio. You need to figure out what the ratio is. And what you then do is, with this ratio, let's say the ratio acid to base is, let's say it's 6. You can also write this as 6/1. This means you need 6 parts acid and 1 part base. Okay? Make sense? Sort of almost like a recipe for a cocktail. Think about it like that. 6 parts vodka, 1 part Coke. Diet Coke. Not the stuff that... Yeah. So once you've done that, once you've calculated that, and as I said, you can do that beforehand, you then can make up a solution. You can, for example, say I take 60 milliliters of acid and 10 milliliter of base. By the way, when you do the calculation, you will find it's not the ratio, it's not 6. It's a different number, but I leave that up to you. You're smart. So you mix these 60 milliliters of acid with a 10 milliliter of base, mix well, check your pH. Would be interesting to see whether you get the same, whether you get the anticipated pH of 6.5. In the last few years, we found that it's pretty accurate. However, the Henderson-Hasselbalch equation is not always 100% accurate, because some buffer systems are sensitive to temperature and also sensitive to dilution. And that is what you're going to do in the next experiment. So once you've done this, what you're going to do is you take, I think, 5 milliliter of your acid and is it? Oh no, forget that. You take your mixture of buffer, and hopefully this gives you pH 6.5. You take this buffer and you dilute it. And the easiest way would by factor 10, dilute buffer factor 10. The easiest way is you just simply take 5 milliliter of the buffer plus 45 milliliter of water. dilute it, mix. And then measure pH. The question is, will the pH of that buffer change after dilution? I'm not telling you what it does, because that's something that you will find out. And then, when you have found out, you tell me what's going on here. Why does it change, or why doesn't it change? And that tells me then whether you understood the whole concept. Okay, happy with that? We need a little bit of excitement in this. Last but not least, what I want you to do is, and that's getting really dangerous, so proceed with caution and safety specs. You take H3PO4, phosphoric acid. It's a medium strong acid, and you add sodium hydroxide to it, stepwise. Instructions are here. Now, you can see H3PO4 can potentially donate 3 protons. So the first step is H3PO4, H plus plus H2PO4 minus. And for this, the pKa is, what is it, 2.15. And you are dealing with a 50 millimolar solution of this phosphoric acid. You can calculate the pH. Is it a strong or weak acid? What do you think? Remember, it has a pKa. It's probably a good chance, if it has a pKa, that's not a terribly strong acid, so it's probably a weak acid. You can calculate the pH with our equation for a weak acid, pKa minus log of the concentration of the acid. And again, you can do that at home over the weekend before the practical, so that you can figure out what is the pH that I'm starting with. You then add some sodium hydroxide, and you measure the pH. You add more, you measure the pH. You add more sodium hydroxide, measure the pH. You do a nice titration. What you actually should see is, and you should plot that, on the x-axis is milliliter of sodium hydroxide added. And on the y-axis you have pH. And what you see actually is, hopefully, something like that. Rather weird curve. Now, there are a few steps in there. You, for example, notice this massive jump here in pH in this region here. What happens in this case here? Well, in this case, all of the phosphoric acid is used up by the sodium hydroxide. All of that is used up. So what you see is now you add the sodium hydroxide and the pH goes up until we reach the next step, until we reach that step. And this has a pKa of 7.2. So in this range here, you run out of the phosphoric acid, and then you basically start again with the H2PO4 step. This step here, pretty much in the middle, is also an interesting step. This is called the equivalence point. And this is when your concentration of phosphoric acid is equal to the concentration of the H2PO4 minus. At that point. Can you predict what the pH at this point will be? Can you predict what the pH at this point will be? Shall I scroll up a little bit to give you a hint? At this point, at the equivalence point, we have the same concentration of acid and base. So our pH will be the pKa. So in this case, the pH is equal to the pKa, which I told you for the first step is 2.15. This actually is quite a neat method if you have an unknown acid to figure out through titration what is the pKa of this acid. All you need to do is you add so much sodium hydroxide so that half of your acid is actually converted to the base. That is the equivalence point. And what you then do is you just simply measure what is the pH at the equivalence point, because that is your pKa. Now here we have H2PO4 minus 2 HPO4 2 minus. And here we have HPO4 2 minus 2 PO4 3 minus. Again, if you add more sodium hydroxide, you come here to another equivalence point. Let's do that in a different color. And this equivalence point, again, is pH equals pKa. That's for the second step. That's 7.2. And finally, you have a third equivalence point here. And that is 12.4. So with this method, you can measure the three equivalents, the three pKa's of this triprotonic acid just by getting the equivalence points. And what I want you to do is you titrate it until the pH is about 12.5. And I want to see that curve. You don't have to do a write-up, but all what I want to see is, in a way, your results in your lab book and this titration on a piece of graph paper for the practical. Are you happy with that? Can you do it? Can we do it?
Yeah.
No. Can we do it?
Yes.
Okay, you still don't know how it works, right? Can we do it? Yes, we can. Bob the Builder. Or Barack Obama. Yeah? So, can we do it? Thank you. And when you have done that, then life is good. I suggest we have a 7-minute break, and then I will go to the assessed practical, okay? See you in 7 minutes.
Can you scroll down a bit, please? Down. Yeah. Yeah, here. Thank you so much. Yeah. Thank you.
Oh, okay. Oh, sorry.
Thank you. The one from the last person. question about the pH probe. If we leave it on solution for too long, does it damage it?
No.
So I can
Absolutely fine. Yeah, you can leave it in there.
just think like maybe if the pH is too high or does it have any limitations?
If the pH gets too high and you store it too long in pH that is either too high or too low, then the probe will suffer. But we are talking about weeks. So a couple of hours.
Because I was thinking about the spectrophotometry.
Yeah.
You know, the spectrophotometry has a limit. If you go over the limit,
Oh, I see. The probes that we are using, they are usually reliable between 1 and 14.
okay.
So, nothing too. Go to the website because there is then of the Bioscience website because there are all the emails, or you can simply email bioadmin account and ask for I don't know that. Oh, I'm sure he has, but I don't know when. Sorry.
Experiment with it last week.
Sorry?
This week. Is it the same
No.
as not?
Totally different one.
Oh, okay.
We want a little bit of excitement. Okay, let's continue. So the practical in week 8, that is the big thing. That's the assessed practical. And no, this is not a practical that you have done before. So it's a completely different practical. Because let's face it, as scientists, we don't want to do the same experiment all the time. We want to do new experiments. And therefore, we need to be able to follow instructions for new experiments. In the long version of this practical, and I've sent you the link to that, you have the assessment criteria for this practical. So can you do it safely? And I will go around and make notes of people who don't wear safety gloves and safety specs. Are your data nicely presented? Are your measurements precise? And how good are your calculations? Right? And that gives you a little bit of an idea what you are supposed to do. Again, this is open book, so please bring along whatever resources you want. If you like, you can print out the long version. I didn't do that because I want to save the trees. You can have that on your mobile phone if you like, or on tablet, or on a laptop if you want to bring that in, but that's at your own risk, right? You have the short version, and that short version is usually enough, but as I said, bring along whatever resources you deem useful. So, what is this practical about? You are basically doing an experiment that you will do many, many, many more times as a scientist. You basically need to determine the concentration of an unknown protein sample. And you probably have done that before. And the way you do that is, first, you create a standard curve. So that's the principle. You create a standard curve, and I know that you have worked with standard curves. For the honey practical, you had your standard and you measure the absorbance of the standard. And ideally, you get a straight line. Something like that. And from the standard, or what you do, you also take an unknown protein sample, you treat it like your standard, you also measure then the absorbance of the protein, of the unknown protein sample, and you do that in triplicates. And from that, you should get 3 measurements for the absorbance, and from your standard curve, you then can immediately read off the corresponding protein concentration of the unknown sample. Now, since you do that in triplicates, we can do a little bit of statistics with it. So what I want you to do is, because you've got the triplicate protein concentrations, the unknown protein concentrations, you would calculate the population mean, the population variance, and the population standard deviation. And I've shown you in previous sessions how you do that, but in the long version there are also the equations for that, how you are going to do that. You also can treat your three measurements, your three unknowns, as a sample where you then calculate the mean, the variance, the sample variance, the sample standard deviation, the standard error of the mean, and the margin of error, and the upper and lower bound of your sample. In order for the margin of error, we said the margin of error is a t-value times the standard error of the mean. The t-value for this, in this particular case, would be 4.3. But I will put that on the board in the lab. And for the rest, there are the equations in the long version. Feel free to bring that in. I don't have any spare copies of that, by the way. So if you want to bring it in, you have to print it out yourself. So that is basically what you need to submit at the end of the practical. There's no lengthy write-up. I'm pretty familiar with the method. You don't have to tell me what method you used. What you need to do is you need to say, these are my data. This is what I've observed, ideally with a table. So you just simply say, this is what I've measured for my standard. Standard measurements. This is for the triplicates of my unknown sample. One, two, three. So these are the absorbances. This is what I read from my standard curve, and you need to submit the standard curve because that is part of the assessment criteria. So your standard curve. These are the readouts. And therefore you get protein concentration of the unknown sample. You get 3 different protein concentrations, or maybe not different. 1, 2, 3. And then you do your calculations, your population. And what I want to see in what you submit is your calculations. I want you basically to show me how you have calculated it. So if you've got 30, 35, and 40 milligram per milliliter, what I want you to do is I want you to write down the equation, for example, for the mean, equals xi over n, and then you say equals 30 plus 35 plus 40 divided by 3 equals 35 milligram per milliliter. That is the way I want to see it. Why do I want to see it like that? Very simple. If you just simply write down standard deviation is 0.1, I have no idea where this comes from. It could be that you're just simply lying. Of course you wouldn't, because you're nice people, mainly, most of you. But I want to know where this 0.1 comes from. So therefore, show me how you did the calculation. Last year, about 20% of people got a massive reduction in mark because they just simply wrote down a number. I need to know where this number comes from. Okay, can you do that, please? Makes life easier for me and for you. You then do the calculation. Everything is on probably 1 page, maybe 2 pages. Please bring some writing stuff with you, graph paper you get. And you staple that. There's a stapler at the teaching hatch. You hand it in before you leave the practical. Job done. You don't need to worry about anything about hand-in date or anything like that. It's all done. Do me a favor, write so that I can read. Yeah? I remember a few years ago we had a final year student who wrote lovely essays. Well, we believed they were lovely essays because nobody could read it. It was slanted to the left, very long and very dense. It looked like barcode. I thought maybe I should go to Sainsbury's and try and scan that in. Maybe it makes sense then. You just simply couldn't read it. If I can't read it, or if it is just all over the place, sorry, I know life sucks. But if I can't read it, tough. Okay, what is actually what I want you to do? And here's the long version. You have, for your standard curve, you need to do 8 test tubes. And then in these 8 test tubes, you've got an exact pipetting scheme. Let me see if I... You've got your pipetting scheme. That is for use a known concentration of a protein, bovine serum albumin, and you add different amounts of this bovine serum albumin solution into these tubes. So for test tube 1, you don't add any protein in it. This is your blank solution. And this becomes important. This is the solution that you use in order to zero your spec. You have done the zero spec thing with Dr. Carden, I believe, or Dr. Mulligan, yeah, in the practical, so shouldn't be too difficult. You then add 0.1 milliliter of the BSA to another tube, and you make it up to 1 milliliter with water, and so on, and you follow the instructions here. So you get different concentrations of BSA, and you can calculate the different concentrations. Your standard has a concentration of 10 milligram per milliliter. So if you don't have any protein in it, your concentration would be 0. If you only have 1 milliliter of that standard, this would be 10 milligram per milliliter. and you can fill in the rest. You can do that in advance. Okay? So that is your standard curve. You also prepare at the same time your unknown concentration. And to do so, you will find that around your place where you are working, and this practical, you work individually. You don't need a partner. You will find tubes labeled A to, I think, F. Each of these tubes has an unknown protein concentration in it. You just take one of these tubes, whichever you want, A or C or, whatever. But you just concentrate on one. You take this one, you write down what tube you used. So you just simply say, yes, I used tube F throughout. You then prepare 3 samples with this F. So you do that in triplicate. And in these 3 tubes, you add 0.2 milliliter of this sample from F, for example. 0.8 water makes up a total volume of 1. Ideally, at that point, you should have 11 samples. 8 are your standard, plus 3 are your hopefully identical unknown samples. Yeah? Can you do that? And each sample should have 1 milliliter in total in it. You then add to this 1 milliliter in each sample, in these 11 test tubes, you add exactly 7 milliliter of the detection reagent, of the Bioret reagent. It's absolutely essential that you mix very, very well. So you could use this whirly mix. Make sure that it doesn't splatter. And you leave it for 30 minutes. Important, leave it for 30 minutes. The reaction usually is done within 5 minutes, but in order to get everything reproducible, leave it for 30. Be on the safe side. And then you measure, and what you will see, hopefully, is that if you line up your samples, the more protein you have in your sample, the deeper blue your samples will be. And that's quite a nice check, because it should go from mild blue to deep blue in your standard, and then you can already sort of see where is my sample, where are my 3 unknown samples. Are they all over the place? That's not good. Does it show quite a nice picture in terms of mild blue to deep blue, or is it very blue, a little bit blue, very, very blue, a little bit more blue, things like that? If it's all over the place, there is basically you effed up somewhere. At that point, you probably can still retrieve it and repeat the experiment. So make sure it looks really consistent with what you would expect. The more protein you have, the bluer it is. Bluer? Okay. Blue, blue, bluer? Is there blue? More blue. Deeper blue. Bluish. Okay. Once you've done that, you add one, you then put the first sample, that's your blank, without protein. You put that in a cuvette, 3 milliliter or so. It doesn't need to be exact 3 milliliter as long as the beam of the spectrophotometer goes through the solution. That's absolutely fine. You put that in the cuvette. You zero your spec with the sample that does not contain any protein. That's your blank. And that should be the palest blue, if you like. And then you measure all your other samples. Yeah, does it make sense? There is one tricky bit in it, and that is your unknown. From your unknown sample, you only use 0.2 milliliter in a total volume of 1. So your unknown sample that you have is basically diluted by a factor of 5. And when you then calculate what is my protein concentration, you need to take that into account. So for example, you see your standard. So here we have 3 milligram per mil, 4 milligram per mil, something like that. And you find that your unknown would indicate it is 3 milligram per mil. That's the unknown. Three milligram per mil. It's the equivalent blue. Don't forget it's factor 5 diluted. So in order to find the original, you have to multiply this by factor 5 to get your true concentration. So that, of course, gives you 14 milligram per mil. Was just checking whether you are awake. And that is what I want to see, right? 15 milligram per mil. Does that make sense? And with these numbers, you do the statistics. Population, you treat your sample as a population, or you treat your measurements as a population, and then you treat your measurements as a sample. And that is what I want as a nice write-up. Assessment criteria are given. And this is basically how you then measure an unknown protein concentration with a standard curve. Pretty much the same as you've done the honey. You've done standard curves with the honey, right, with the glucose standard, so it should not be too difficult. The instructions are pretty simple. I was just saying before the lecture, I'm pretty sure if a 10-year-old would understand how to do the pipetting and how a spectrophotometer works, following the instructions, they would be able to do that. Perhaps not the calculations, but the experiment itself. In total, the experiment, time-wise, it takes you probably an hour to get your readings. It hopefully takes you half an hour of doing the calculations, 10 minutes of stapling. So hopefully, in less than 2 hours, you are out of this assessed practical. Happy with that? Yes, question? Sorry? We have staplers. But if you want to bring your own stapler, please do feel free. Yeah, it's open book. Bring your own stapler if you like. This is how you measure unknown concentrations with a standard curve. At least this is the method for undergraduate students. For the professionals, they will tell you that this method with a standard curve and just reading of the standard curve is wrong. Why it is wrong, I will discuss with you when we talk about regression lines. But I don't tell you actually how it's done properly, because that's dark magic. That's really bad stuff. I'm not going to teach you that. Any questions? Shall we try again? Can we do it?
Yes, we can.
Can you now go into the holiday without worrying? Go in peace.